Hello everyone, I am Shashwat Khandelwal from the Reconfigurable Computing Systems Lab at Trinity College Dublin. I will be presenting our work, Quantized Neural Networks as Low-Power Intrusion Detection Systems for Automotive Networks. This work was done by me and Dr. Srijit Shankar. In this presentation, we will first talk about automotive networks. We then look at what is controller area network and what are its vulnerabilities. We will then see what the existing solutions as intrusion detection systems for these vulnerabilities are. This is followed by the constraints that these intrusion detection systems face in resource-constrained vehicular environments. This will be followed by our proposed intrusion detection system architecture. We then conclude our presentation with experimental results and conclusions. Automotive networks. Vehicles today contain more than 50 electronic control units to enable advanced driving assistance systems or ADAS applications for comfort of passengers. Robust automotive networks are therefore used to facilitate reliable and secure communication between these ECUs. Depending on the application, multiple networks serve this purpose in a vehicle. These are local interconnect network for body-based applications such as controlling windows, mirrors, etc. Media-oriented systems transport to connect audio, video, and other multimedia components in a vehicle, allowing them to communicate and share data. FlexRay. This is a time-triggered deterministic automotive communication protocol used for ADAS systems and other safety-critical applications. Controller area network is used for communication between ECUs for critical communications to support applications like engine and transmission control, airbag deployment, and anti-lock braking systems. Automotive Ethernet for diagnostic purposes and fast communication between ECUs and the sensors on the vehicle to sometimes determine how they function in real time. Out of these applications, we focus on the controller area network safety, as this network carries critical communication messages between the ECUs and has vulnerabilities that can be exploited. Controller area network, or CAN, caters to both critical and non-critical functions in vehicles. Introduced in the mid-90s, this network quickly became an industry standard due to its high-speed single-wire bus mechanism, which cut down the wiring costs in vehicles significantly. It has certain unique features, like priority-based mechanism for sending messages on the bus to make sure all critical messages meet their latency deadlines. To save wiring costs, it is implemented in a line/bus topology where the bus acts as a medium for communication between ECUs, meaning it has a broadcast-based mechanism for sending messages to facilitate communication. It offers network bandwidth in the range of 125 kilobits per second to 1 megabits per second and can be implemented as both one-wire and two-wire. What are its security threats and vulnerabilities? Controller area network was designed for closed networks. It was hence considered secure when it was initially deployed in vehicles. The increased connectivity to the outside world to enable ADAS applications, though, exposed vulnerabilities in this network. These can be exploited to gain access to critical vehicular components and can risk safety or loss of personal information for passengers. Now, attacks due to these certain properties are as follows. Due to the broadcast-based communication mechanism, the sender broadcasts a message to all the ECUs on the bus, meaning an infected ECU can gather critical network or user information by sniffing these messages. Or lack of sender authentication can cause active injection attacks like denial of service and fuzzing, which can fully disrupt normal vehicle functioning, as shown in the figure on the bottom right, where the brake control module fails to receive a message from the engine control module in case of a denial of a service attack, where the compromised ECU floods the bus with the high priority messages. A very famous example of CAN hacking was shown in 2015 in the hacking of Jeep vehicle. Here, the hackers were able to take control of the full vehicular functioning with the driver inside on a national highway remotely. The existing solutions that have been proposed to mitigate these vulnerabilities are in the form of intrusion detection systems. Early intrusion detection systems were rule-based, which meant that they could not identify new attack vectors. They also incur incremental memory storage for each new attack. Machine learning models have thus been explored as intrusion detection systems due to their generalizable nature. Recently, machine learning models have been trained to flag discrepancies in the network traffic. Various machine learning architectures have been implemented as intrusion detection systems, like deep convolutional neural networks, generative adversarial networks, convolutional LSTMs, and even classical techniques like SVMs and decision trees have been developed to make these systems robust and accurate. Now, even though these models have been highly successful in various attack vector classifications, there are certain obstacles, though, on how these models need to be deployed in a resource-constrained vehicular environment. We discuss these next. Usually, software implementations of these models, of these machine learning, high memory intensive machine learning models, leads to sharing of critical compute resources on the ECU, which can lead to computational overheads in actual ECU computation or cause isolation issues. Standalone ECUs as IDSs suffer from weight cabling overheads depending on their integration architecture for the ECU, while power constraints in this environment restricts the use of powerful GPUs to perform line rate intrusion detection. So, based on these challenges of security with controller area network and the constraints faced by intrusion detection systems to protect them, we propose the following as our ECU intrusion detection system architecture. To solve the whole problem of intrusion detection in a more holistic way, solving the constraints of accuracy, latency, and power consumption, we present a multi-dimensional FPGA-based intrusion detection system architecture. We demonstrate this architecture on a system on chip, which acts as a hybrid IDS-enabled ECU. The SoC itself is divided into programmable system and programmable logic. Here, the core ECU functionality is carried out in the PS part of the SoC, comprising of automotive-grade quad-core ARM-A53 processors, while the IDS computation is offloaded to the PL part of the SoC, which communicates with the ECU via the AXI interconnect. On the PL, we can have multiple intrusion detection systems that scan the incoming CAN packets for denial of service, fuzzing, or other attacks simultaneously. The intrusion detection systems in our work are trained using Brevitas, a quantization-aware training library. The models trained in Brevitas are exported to the FPGA using the FIN toolchain. The FIN flow generates low-level drivers for interfacing RIP from the ARM cores on the Zinc device over the AXI interface. Once deployed, these intrusion detection systems can inform the ECUs to take mitigation measures in case of active attacks. We now discuss the experimental results of our paper. We tested our intrusion detection system with 50,000 messages for each of the two attacks, denial of service and fuzzing. From the accuracy metrics, we see that the intrusion detection system gives near perfect classification accuracies for both the attacks, denial of service and fuzzing, with only slightly higher false positive rate for the fuzzing attack. In terms of message processing latency, to process one single CAN message, we report a latency of 0.12 milliseconds, which is 4.7 times lower than the state-of-the-art intrusion detection system. This translates to a network bandwidth speed of 896 kilobits per second. We find that the entire intrusion detection system scanning for denial of service and fuzzing attacks, a single instance of this model consumes less than 4% resources on average, leaving enough for other ECU functionalities that can be accelerated on the FPGA. Moreover, multiple such intrusion detection systems can be deployed due to the less number of resources which our single model consumes. We report 2.09 watts as our active power consumption during this intrusion detection, which translates to an energy consumption of 0.25 millijoules to process per one message. Conclusions. In this presentation, we presented a hybrid FPGA-based IDS ECU architecture for automotive controller area network. The proposed intrusion detection system achieves an average accuracy of 99.95% for denial of service and fuzzing attacks. We find a 4.7x decrease in message processing latency as compared to the state-of-the-art, with only 2.09 watts active power consumption. We believe that this proposed architecture can enable further research towards line rate distributed intrusion detection for controller area network and other faster networks like automotive Ethernet. Thank you, and I look forward to all your questions. You can also contact me at my email address khandels@tcd.ie. Thank you.